Hello, today we will talk about system stability. There are two types of system stability, external and internal. External is also known as BIBO and internal is known as asymptotic. BIBO stability means if every bounded input produces bounded output, the system is BIBO stable. In contrast, if even one bounded input results in unbounded response, the system is BIBO unstable. Like here, even one bounded input is giving you the unbounded response, then that system will be BIBO unstable. So in order to check that the system is BIBO stable or not, if its impulse response, how we can check that the system is BIBO stable or not. So we can check in this way that if its impulse response h of t is absolutely integrable, the system is BIBO stable. Otherwise, it is BIBO unstable. So this is the formula. This is the sufficient condition for BIBO stability, that the absolute integral of h of t, that is impulse response h of tau over minus infinity to plus infinity. So if it is absolutely integrable, then it must be less than infinity. It means it has some upper bound. It is bounded. It is not tending towards the infinity. Then the system is stable externally. Now, the other type of the system stability is the internal asymptotic stability. It's mean, suppose a linear time invariant system is in zero state and we change this state by creating small non-zero initial conditions, small disturbances. These initial conditions will generate signals consisting of characteristic modes in the system. So if the system is stable, it should eventually return to zero state. In other words, when left to itself, every mode in a stable system arising as a result of non-zero initial conditions should approach zero as t tends to infinity. However, if even one of the mode grows with time, the system will never return to zero state and the system would be identified as unstable. In the borderline cases, some modes neither decay to zero nor grow indefinitely, while all the remaining modes decay to zero. Such a system is said to be marginally stable. Or in simple words, we can say this thing, that if the characteristic roots for a system is in LHP, then it is internally stable. So the main condition for a system that is in internal stability, asymptotic stability, so we can say this thing, if and only if all the characteristic roots are in LHP, left hand of plane. The roots may be simple, unrepeated or repeated. And for the other, like unstable system, internally unstable, a linear time invariant system is unstable if and only if one or both of the following conditions exist. At least one root is in right hand plane. There are repeated roots on the imaginary axis. So even if one or both conditions are there, so the system is unstable. And if there are no roots in the right hand plane, but there are some unrepeated roots on the imaginary axis, so that system is known as marginally stable. So how we can check? Very easy. If you need to check that linear time invariant system, here in this example you can see it consists of two subsystems, S1 and S2 in cascade. The impulse response of these systems are H1 and H2. So it is given here. So how you can check that it is stable, BIBO stable or not. So you can take the convolute, and after you can observe this thing that it is the impulse response is absolutely integrable. You can observe here it is absolutely integrable. So you can say this BIBO stable. So now in example 2, investigate the asymptotic stability of the linear time invariant system described by the following equation. Very simple, what you need to do, you just simply first replace the d with lambda, and then you need to find the roots. So here you can see you are getting lambda equal to -1. So it's mean it is in the left hand side of plane. Similarly, you can check the other roots as well. So when you solve this, so you will get -2 plus minus j2. So it's mean it is also on the left hand side. Minus indicates that it is on the left hand side. So you are getting all the roots on the left hand side. So it is asymptotic stable or internally stable. Similarly, if you solve this equation, like here, first you get 1. It's mean it is on the right hand side. But other roots, if you check, they reside on the left hand side. And you can show this, you can create a plane, and then you can show one is, so this is marginally stable function. Thank you.